I'm Aastha Pandya, Chair of IEEE Student Branch at Acropolis Institute and the host for the today's podcast. So last year at podcast featured inspiring conversation with Indian professionals, and this year we are taking a global step and we are trying to connect with global leaders. So yeah, additionally we would also like to highlight our achievements also that we have got the award for the best student branch 2025 from the Indian Council, and our branch counselor, Dr. Gaurav Chaitanya sir, received the award for the best branch counselor 2025. So today we are honored to have you as our distinguished technology leader and 2026 chair of IEEE Central Illinois Section and an industry expert. So, I want to give a quick introduction of yourself that we have researched to our team, student branch. So, Darryl sir currently serves as the control system team lead at the Caterpillar INC, where he drives innovation and committee secretary at IEEE at the Standard Association, and government relations chair of Region 4 is truly remarkable. And he also serves as associate editor for IEEE transactions on industrial informatics under the IEEE Industrial Electron Society, contributing directly to advancing global research in industrial automation and informatics. So, we are excited to explore your journey from a reformed astrophysicist to shaping the industry standards and IEEE initiatives worldwide. So, welcome, sir, to the podcast. And we are heading up to the episode 3 now. So, the topic for today is AI robotics foundation models. As artificial intelligence rapidly evolves, foundation models are transforming how intelligent robotic systems perceive, learn, and interact with the world. So let's get started with our first question. So you had multiple leadership roles across the section, society, and global initiatives. So how did each stage of your IEEE journey shape your professional and also the personal growth?
Well, first of all, thank you for inviting me. There's some awesome achievements you have for your student chapter. So that's awesome. So I started with astrophysics, I guess, like all kids, interested in dinosaurs. Probably by the second grade, I went to a library. I got a book on ABCs of astronomy. It was an oversized book, and I looked at it, and that was the first time, my vision of, I guess, the universe was expanded. And so that's what drove me into astrophysics. And I actually interned at NASA. I worked at NASA in multiple ways as an intern, as an employee, as a research assistant, as a consultant. Just about any way you can work with the government, I've done it one way or another. And so about my IEEE journey, I switched from astrophysics because astrophysicists don't make money. It sounds cool, but you can't eat. And so I always was interested in problems and simulations, right? And so I switched to computer science because I wanted to still address those, NP hard, NP complete type of optimization problems. And so during my time at university, I started, hanging out with engineers. So I was in computer science, which technically was in the School of Business. And so unlike most people in business, I had to take calculus, I had to take physics. And so there was this disconnect somewhat with people in my school. I didn't have to take business. And so I hanged out with engineering, and I think I was a junior at the time, and they were having an unmanned autonomous robotics competition. So that's done in the 2000s. This is in 1995. We were doing autonomous robots for driving. And that gave me a lot of application of software, seeing software move something, right? And then in my senior year, I actually was chair of IEEE. And so it really, bridged that gap of computer programming, actually making real machines move. I got more interested in factory automation. I wanted to make bigger machines move. So I did stuff for automotive. I did work for variable speed, variable frequency drives with a company called Danfoss, winning up to like 1.5 megawatts. So the largest drives in the world. So you're talking about motors that run, shipping cranes in Saudi Arabia, and some of them run large oil derricks off the sea, in the sea area. And so after that, changed again. I don't know how much you know about United States and healthcare, but United States has many rooms for improvement in healthcare. And so I switched and created a healthcare AI company. And I got funding for that. I had a pilot at Cleveland Clinic, which is one of the premier hospitals here in the United States. Got funding in Silicon Valley. One of the companies that funded us was Singularity University. So have you ever heard of SpaceX? That's sort of the sister organization that came out of. So we were more on the humanitarian side because we were healthcare. And then there's more consulting, and then I got involved with Caterpillar, right? Because again, I'm drawn to big machines and the positive effect machines can have in the world. And so during each of my stage, really, IEEE is important. One, for networking, because you will meet some very interesting people, not just in the United States, but internationally. And also for that adaptability. I guess the biggest thing now they talk about is agility, right? How quickly can you adapt to something new? Because there's always something new. And so in school, you might have the luxury of saying, I'm just software, or I'm just electrical engineering, or I'm just mechanical engineering. But in the real world, you have to have some understanding of each one of those to succeed, along with how to deal with teams.
Yeah, that's a great roller coaster of your journey from being like it sounds very cool.
Thank you.
Yeah, it's a great experience. So moving ahead to the next question, uh, how do you see IEEE evolving in the next decade and that staying relevant in this fast changing technological landscape?
So one of the projects I'm actually starting now. So one thing with IEEE, they have a lot of documents. It's very academic, right?
Hmm.
But we're engineers, or I don't mean engineers just degrees. Engineers as far as people who work to solve problems of humanity, right? That is the basics of engineering. And so a lot of times when we work or see something, we always think of how to improve it, right? Oh, this doesn't work. Maybe they should look at this. Or this doesn't work. Maybe they should add this. But there are some problems that we face in the world that we see that we don't know how to solve, that we throw up our hands and we wait for someone who's a superhero to come and fix. And we have various technologies to do it. And so when I see IEEE, I see them more addressing these humanity issues. So one of the projects I'm working on is actually on flood resilience. And because of the issues that happened in Sri Lanka this year, there's massive flooding that happens in India and China. And so a lot of the impact on these areas, when you have these, especially these isolated communities, are devastating, not just from the flood itself, but the aftermath of the flood, right? It takes a long time to move in resources. It takes a long time to help people. There's lives that could be saved, prevented from dying after the flood, right? Because people have issues going to the hospital, getting care, getting food, disease. All of this happens. And so there's already a lot of research out there for AI modeling for identifying at-risk communities. There's a lot of research already for identifying the effect of flooding to power distribution, communication networks, roadways. But the problem is it takes so much data to gather that literally there's no money in it. I mean, it kind of sounds bad to say, but if you think of all the business models, right, it's very hard to have a business model that makes money saving lives, right? And so when you look at IEEE and its benefit and with its network and with its students, and even with this initiative I'm talking about, it's really, activating engineers to be a part of solving this problem that people think is too complex, but it's not too complex. It just requires that shifting of saying each person can contribute to the pains, their problems, their society, people they care about have. And so I see IEEE shifting in that side from saying, working on these large scale, long duration projects that actually affects the members of their own society.
Yeah. Okay. So thank you so much. And with the moving to our question, the next question. Yeah. So how do you see the convergence of AI robotics, cloud computing, and edge intelligence shaping the next few years from IEEE?
So when we're looking at this, let me dissect this first. So when you're talking about AI, right, agentic AI is probably only one out of the 20 23, I think, is more than 20 different types of AI. And so that's the flavor of the day. Um, some of the requirements for agentic AI are very large as far as memory, as far as training, and that will come down in a while. But some of the things that they say, like hallucinations, right? Is it part of the way of training it, or is there some way of overcoming it? And so when we see that side, the limits of agentic AI is one thing, and in the real world, it's something where it could accidentally, smack your kid or something else like that. You don't want a robot attacking your kid. And so you want safety nets around it. And so how to do agentic AI with a lot of safety nets and precautions around it? Because I don't know about your household, but mine is not organized. And so while roads are somewhat chaotic, my home is probably more chaotic than that. And so to have a robot companion that can wander or interact with you in close proximity and your loved ones in your house, some houses that might work nice, some other houses that's not going to work nice. When you look at cloud computing, I think cloud computing has a lot of great potential, at least for allowing people to access and create large-scale models that might not have the physical infrastructure to do it, right? So when you're looking at certain countries, they can afford to make data centers. Other countries can't. And so you want them to have the expertise and ability to do it, to create and train these models. Because as we go into more like housing, right? Houses in the United States is different from houses in other locations in the world. And so if you're talking about making a targeted robot, it would have to probably be somewhat targeted, not just to language, but to culture, to how architecture and construction is different. And it will allow that to happen, right? The first question was with IEEE as part of this too. I think you were talking about it. So when looking at IEEE, the interesting thing about it is the different pieces of it is being investigated, different pieces, different aspects of it. So one thing is, AI. The one thing that's big now in AI is how do you create AI that can forget, right? Because you have a lot of AI. Well, I'm going to train it so you remember this. I'm going to train it so you remember that. But normally, if you think about how humans remember, something that has a negative feedback, usually you tend to forget. So it's like, well, I have this generic AI algorithm that could be this robot in this household, but in my household, it has to learn what I like. It has to unlearn what I don't like, so it doesn't do that again, right? And so there's a lot of ways where you as an individual or student could go in and research, look into that areas, look into, because that one is more industrial electronics side than computer society. Power and energy is also an aspect of it. We're going to talk about charging. And so reading the different papers that's available, even from your school, interacting with different people, different sectors, you can identify, this is an interesting application maybe in this field that you can use for robotics in this other field. Because they're using robotics, I mentioned household, but it's also for industry. It's also for medicine. It's also used for assisted living. And so each one of these applications is still robotics, but they're slightly different.
Oh, yeah. So like me as an electronics student, it's very informative to get more diving into this field of robotics. Yeah, let's move further to our next question. So do you believe that foundation models will lead the general purpose robots that similar to how large language models changed the software?
To that one, I would say yes. So I think that some of these foundation models, I don't know if you've seen the new one. There was one that just came out of China. I think they had their press release maybe 2 or 3 days ago. And it was a robot that was doing household chores, like moving glasses and cups out of a sink, getting milk out of the refrigerator. And I think it was done by Alibaba, actually. They have a AI research arm there too. And even though, it was time lapse, because of course it takes time for a robot to move, it did some extraordinary things that you would say would be human-like intelligence for it. Because you would give it a text sentence and it will actually complete the task and learn how to complete it. And so I think this will help change the way we interact with technology. Because, a lot of times when you look at cell phones, you look at other things like that, right? We had to adapt to the technology, right? LOL was not a word 23, 25 years ago. It became a word because it's easier to text and all this other stuff. And so there's a lot of adaptation that we have had because there was limitation on screen size, there was limitations on bandwidth, all of this stuff happened. But once you have a robot that you can interact with in the real world, you can interact with them as almost in a human-like way, right? Because only some parts of our communication is speech, right? We communicate verbally, we communicate non-verbally, we communicate with inflections of words. There's all these nuances that we're used to doing. And the more that we can use them, the more that it doesn't affect how we communicate with people, right? Yeah. Our over-reliance on text messaging makes us talk to people differently, makes us have relationships differently, right? It changes our interaction with people because we have to interact this way with machines. But I think this robot gives us the capability of not losing that and being able to express our humanity with machines, just like we express it with other human beings.
Yeah. So, like you describe yourself as an astrophysicist. So,
Yeah.
like, could you tell us more about the transition that what led you into control systems and industrial technology?
Yeah, so originally when I went into astrophysics, I wanted to do stars formation. I did work with stars, galaxies, how they're formed, how they're destroyed, how they age. That was my focus. When I did work at NASA, I also worked in other areas. I worked in space electronics. So that was simulating failure modes in space components and effect on communication. And then I did some non-destructive testing and evaluations. This is more material science, where we had space station components, and we have to have a way of detecting surface cracks, subsurface cracks. Because, when you mold it, there could be these deformities that are minor. But like if you take the International Space Station, right? It goes around the Earth, I think, every 18 hours. So every 18 hours, it goes from probably, plus 200 degrees to minus about 200 degrees. So it has done thousands of thermal cycling, right, over the 20 plus years it's been in orbit. And so normally you get material failure, fatigue, do that thermal cycling. But the International Space Station has held up quite well, being that it has had to go into that each day. And so a lot of that I was interested in. And when it transitioned more to industry is when I looked at factories, right? You have pieces moving, and you had to simulate, how these materials are moved, how do you operationalize it, how do you optimize them, how do they interact with human beings because you have to make it safe. That became an interesting dynamic because people are involved, right? You're looking at the operator interaction with the equipment. And so that was what drove me to that more. And, even when I did the stuff with the drives, it was more like, how do you make it friendly? Because when you think about it, there's a lot of complexity in the technology we use. There's a lot of ways that someone can use it wrong. You expect someone is paying attention, but people sometimes don't pay attention, and they might not pay attention when they're operating something that's 10 tons. They might not have focus. They might not have slept the night before. And so when you're like, oh yeah, I'll have 100% focus. I mean, really, do you really have that? I mean, I have a car, and I have a number of cars. Has anyone read their car manual from end to end? No one reads their car manual. But we all operate it. But you talk to the auto deal, the like when we make stuff for like other stuff, like for drives or operating machinery, we're like, it's in the manual. They're like, yeah, like they would read the manual. The only time you read the manual is when it doesn't work, right? And so now you're talking about how do you like identify those things that the people know intrinsically and make it easy to meet people where they are. because people are busy and they don't do this. And so working on larger machines with larger risk, it became interesting because at the same time you identify how can you make it safer for human beings to operate if you don't have 100% of their focus. And that's one area that intrigued me and kept me involved with that entire systemic point of view, right, of that issue.
Okay, so like that was more towards the humanitarian purposes and more safer models. Right?
Yes.
Okay. So the foundation models are becoming a major topic in AI and nowadays. So for our student audience, like sitting and listening here, how could you explain what foundation models are? Like, what are they?
So when you look at the different models, like large language models, right? They're big. They require a lot of resources. It's software. It's virtual. Whenever you're talking about doing anything that's in the real world, especially when we're talking people, like I was before, safety is critical. You have to not only make it safe for things that can fail, you have to make it safe for things that are known too, right? Like if you wrote something for an airplane, right? You assume airplanes will fly right side up. Airplanes sometimes, unfortunately, become upside down in flight. And so if you say, I have this great foundational model where I assume this robot is walking, and interacting with people, what if it's slipping? What if it's not even walking? What if it's on its back? What if it's upside down? Why would the robot be upside down? I have no clue why the robot would be upside down. But if it's upside down, the worst thing you want to do is kill someone. All right. And so when you're looking at a lot of this foundation models, a lot of it, you not only have to look at the ideal case, you also have to make sure you train it for these corner cases, and you at least know where the safety area works and where not. And a lot of the stuff with the training, you have to, like when you create the training for foundation models, you have to make sure you have realistic training. A lot of them are using imitations, so you have to imitate a human being, right? So you go in and you're like, do the task right, do the task sort of right, do the task whatever, and see where that bottleneck is for that, and maybe create something around it for a safety side for it. So like maybe a human doesn't get close to the robot or something else like that. There's a lot of different models out there that merge. Like if you look at the active chunking transformer, if you haven't looked at that, that's pretty interesting. And the only reason active chunking transformer, I think, came out of Stanford 2023-ish. You look at the paper for that, it's on GitHub. That's interesting because it has a fin on one side and it has more of a general position motion ability on the other. And the reason it's interesting is normally large language models, just language, right? Using a convolutional neural net, which is based on vision, right? I have these layers that the data works through. So think of it like, let me give an example. Playing cricket, right? You can hit a ball in cricket. I'm not that familiar with cricket, so I try to explain this here. So you could actually, if you're a batter, you could hit in cricket. And so the way you actually swing for how far you want to hit the ball, hit the ball or not, is something that you learn and you practice, right? It doesn't matter if you're doing it in India, it doesn't matter if you're doing it in the United States, it doesn't matter if you're doing it on an indoor court, it doesn't matter if you're doing an outdoor court. That type of swing is one thing. You can even swing in the dark, right? The other part of it, if you swing in the dark, you're not going to hit what you want to hit. That's the reality of it. So part of it is knowing the motion of how to swing, depending on what you want to do. The other part is seeing the actual world so you could swing and hit the ball correctly. And so the reason active chunking transformer is interesting is because it actually splits in those two parts. One part is actually, using the vision aspect of it. The other one is actually knowing the motion, right? This is how you swing when you want to hit a ball. This is how you do the swing, immaterial where it's at. And so it's knowing the position of where the robot arm is, knowing how much acceleration is, all this pose information. Now you have to take that and apply it at the right time using vision. And when you look at most of the robot foundation models, at least some of the new ones, and they split it up in those pieces, it allows faster training. It allows an easier way to look at it. Some of them are mixing it with, if you did PPO before, it's an older algorithm. It's a policy proximal optimization, I believe is what it stands for. And so if you look at the way they were trying to do autonomous car driving like 15 years ago, it's a system of like an actor critic model, right? I'm gonna maybe 20 times a second or 50 times a second, I would take a picture of where the car is as far as from the driver's point of view. I would decide if I turn left, right, go straight ahead. I would decide what speed it is. It's very simplistic. So instead of mapping the full journey together, usually it does it in iterations. If for this iteration, this is the optimal way to drive. For that iteration, that's the optimal way to drive. Sometimes it's painful because you can do a hard left and a hard right rather than a soft left and stuff like that. And there's ways of trying to make it work. But that model is very small. It's very predictable, but it's not very intelligent. The other side of it is when you're looking at the SIN model, the large language model, it has so much intelligence, almost super intelligence, right? It has more intelligence than we give it, depending on if you train it right. And so mixing those two together is something to learn how that works, because that is probably what's going to be the final way of making this work, right? You want to have the intelligence of understanding language with the security and predictability and safety of something that has defined behavior and borders, right? So I would look at the active chunking transformer. Hugging Face is a good site. If you ever go to Hugging Face, there's a lot of stuff, source code that's out there for that to use. And that's what I probably recommend for your students to play around with. I know there are some robot arms, and I think they're probably $300 list price or something you can get. So you can start, experimenting with some of the most cutting edge AI robot foundation models that's out there in the world today with about $300 of hardware.
Yeah, they are quite expensive also in India also. They are very much expensive for the people, and like humanitarian purpose have lost. It's just getting over businesses and all. So yeah,
Yeah. Yeah, I mean that's the problem, that when you're talking about playing around with these tools, you can do it in simulation sometimes, but actually, like when you see it and you play around with it, you not only see when it works, but you see how it fails. And as engineers, we need to know the border of not only when it works right, but how it fails and why it fails, and how do we overcome that. Right?
thank you, sir, for this. We've got much clarity about it also. So, like, how are these foundation models like different from traditional AI machine learning models that are used in robotics?
So I think, like I briefly went over before, machine learning models, they are made to be run on the edge. Usually they're very optimal for their purpose, right? They can expand pretty much outside of how you train it. They can be very brittle, very single purpose. And so the problem is, it works nice when you have a controlled environment, right? Let's say I'm doing some robot and I have maybe manufacturing, and I know this is the only robot in the work cell. I know it's going to do 10,000 tasks. I know these tasks are always the same. There's low variation. It works nice. It works well, right? Because anything that doesn't match the way you trained it, you could say is error. It might not be error, but you could say it's error, right? And sometimes for these machine learning ones to work, even lighting is important. I mean, if you've seen some areas, they're like, you gotta use the right color light, you use striped lighting, you use all of these things to remove all of these anomalies so it works right. In the real world, it's like, why are you going to have, $50,000 to have lighting for the robot? That's crazy. Or why are you going to say this robot is only going to make one part? You look at most factories now, they make 3 parts, 4 parts, 5 parts. Maybe a new part comes in, or a new adaptation that looks like another part, right? Before it was like, I'll train it on this part, which is Rev 1. If I come up with Rev 2, oh, geez, I'm going to have to train it on Rev 2 or Rev 3 of the same part, just by changing it slightly, right? If you use the non-machine learning, the more intelligent ways of doing it, maybe there's a 4 or 5% difference in the way your part looks or orientation to it. It might still work well enough. Let me put that way, work well enough for it to work. So in the real world, they're more adaptable, right? They're more universal. And so the first thing you have to do when you look at something is see how universal does it have to be, right? Because some people will over-design something. I mean, it's easy as an engineer to over-design something and say, you know what, I could create a machine learning model, I could push it down there, it can run in 2 gigs of memory. Some machine learning models runs less than that. You know, if you have a cell phone, the reason cell phones are now optimal for power is there's machine learning to run the power optimization on Android. It's in there at the low level. So it actually will power down various parts of the processor depending on your usage. And that runs in like, I think, 15 or 20 kilobytes. It's very small. On the other side, if you're going for more adaptability, instead of having gigs of memory, you might have tens of gigs, hundreds of gigs. And so for that cost, right, for that complexity, you have to evaluate what value you're getting out of it, right? And so as we're talking about engineers and learning it, you have to know more than one tool, right? You have to know which tool is right for this problem, because if you're going into something that doesn't have a lot of resources or they don't have a lot of material, maybe a 5,000 robot is good. You go to this other place, it's $5,000 for the NVIDIA card. Sorry, old NVIDIA card. If you want a new NVIDIA card, that's more like $25,000. So if you're saying for this robot, I need to buy a new NVIDIA card, you're probably talking about a $300,000-$400,000 robot, right? And not all factories can absorb that cost for that robot. You know, and not all cultures can. So yeah, so that becomes hard.
Okay.
Yeah, and so it's like for students to know the entire gamut of all of it and the purposes for it. Yeah.
Okay, so foundation models are particularly important for the future intelligence robotic systems.
Yes.
Right?
Yes, it is. For those that are not memory constrained. But you should know machine learning too for those that are memory constrained, yes.
Oh, so we hear a lot about like foundation models in software and languages.
Yeah.
So how could you like see them shaping the real world robotics and the autonomous machines?
I would see that it will be the dominant player to know. So it will shape it in the sense of when you're talking about right now they do simulation work, but when you're saying real world interaction, stuff that Google DeepMind is looking for, understanding the world, like understanding fruit and things that we see in your household, that will be the driver. Because you in your house, right? You can't say sometimes it sees your cat, sometimes it doesn't. Sometimes you might pick this fruit, sometimes you pick another. Not all fruit look the same, and so it because of that uncertainty, that basic uncertainty that's in various locations, that would be the one to know for household robotics, right? That would be the one to know for autonomous vehicles out in the real world, right? If you're talking about the side, like I said, that's constrained, like sometimes in factories and stuff like that, that doesn't have to be the only model. You could constrain it. You could decide if you want, you know, the walls of your factory to be white only, paint them white, and you can make it work, or paint them blue. It's not like the walls of your factory going to be random color. The walls of your house is going to be random color, right? And so one you can find and one you can. So this is why you have to pick up which you want to use and not over design it. But I think most of the value right now, hard AI assistance for the home, that is going to be, or for the hospital, or for walking around the factory office, that is going to be where it's at. Right.
Okay, so do you think that future industrial machines will be more collaborative and they will work along with the humans rather than just replacing humans?
The problem is not technology always shifts humans job skills, right? They don't necessarily replace them. So the robots are going to require more people to service them. You're going to have more skills to service them, more skills to design how to use them, more skills to identify which are the right robots or not, right? And so I don't think it's going to replace the workforce at all. It would change how we interact with it. It's like the calculators displaced teaching math, but it didn't. The concepts of math we do, even with calculus, is what, 1880s or something else out in school. When you get beyond school, some of the concepts you have are very complex, and this is why I use MathWorks or MATLAB, right? You don't have the time to solve it by hand, right? You're seeing so many you're dealing with. And so I see that as happening too with this side, is that it's going to enable people to create more complex devices, more complex things that we haven't created before, right? And yeah, I mean that's pretty much what I have to say about that. So I wouldn't be afraid of it. I would just look at the opportunity. I still want my flying car. I mean, I don't know if you want flying car, but EV cars required a huge change over mechanical, major shift. And people want fuel cells. People want different types of technologies. People are talking about small, not just nuclear or modular reactors, but can you now have nuclear batteries? Can you now have other things? So just like fire is not safe, and we harnessed fire, people are afraid of nuclear energy. But can we harness nuclear energy? We might be able to 50 or 100 years from now.
Yeah. That's, yeah, correct. Exactly. Okay, so like we're moving to the next question. So, what skills should engineering students develop today to work in AI-driven robotics and automation systems?
So this goes with the skill is you should know a little bit of everything. You should be an expert in your field, but you should at least be able to sell to your employer that you know some things of other parts of other things. So if you're electrical, you also have some experience with doing software. If you're mechanical, have some experience using MATLAB. Some experience doing programming, not much, but some understanding of it. Have some understanding of cybersecurity. Because now we're talking about robotics and other stuff like that. There's going to be software on it. So how do you design it to be secure? Because people can hack the Wi-Fi. People can connect via your debug port, right? And so it has to be safe by design, right?
Yeah.
And so when you come up with the requirements, you have to, this is like you do failure mode analysis, right? A failure mode would be, how could someone hack this? Do I want to just secure it by, having the hardware interface not populated? Well, someone can like use jumper circuits to, create those if you do good with electrical engineering. Do I want to design it by some software with Wi-Fi? Well, people might be able to get around that too. Do I want to design it by using digital twin technology? Do I want a software simulation of this so when it knows where the software simulation, the real world diverges, that it's different? So that it could be either one. And so you have to know a lot of it. You also have to be agile to learn what's happening and what's happening not only in your area, what's happening in this in other adjacent fields that affects this. Yeah.
Yeah, so the future engineers need both the software and hardware expertise together.
Yes. Cybersecurity also.
Okay, cybersecurity.
Cybersecurity is very important because there's a reason. I mean, people might want to hurt people or take control of things, especially expensive things, and you have to design it to be safe. Some people hack into things just for fun. I mean, when I worked in healthcare, they had an issue where hospitals would be hacked into and people's medical records would be changed for fun. There was no monetary incentive at all. And so that is the problem. Yeah.
So, what advice would you give to the students from engineering regions and emerging technologies to work in global technology companies?
You need to be able to go in and, like I said, demonstrate you have multiple skills. You need to go in and at least have some understanding of different cultures because most global companies, you have to realize that, some cultures act differently or run differently and what their expectations are. Um, and you need to be adaptable. So, I mean, the other thing is it's hard sometimes being as an American to be patient with people who are not American. But the reality is you have to be patient because you might have an understanding or expectation of how they act. or what this means when they act this way, and you misinterpret it, right? And there's a lot of miscommunication activity happening. This is why you have to be able to connect with people on a personal level, not just technical. And having those skills become more important the larger a team you have and the more diverse team you have, right? So also look at those teamwork, also look at how do you deal with difficult people, because a lot of engineers, especially the ones we're talking about, especially ones who are very gifted sometimes, they're very difficult people to deal with. As you probably know from taking student design classes, you have coworkers that are probably, or students that are difficult to deal with, right? Yeah.
So, how important are internships, research, and IEEE involvement compared to the academic grades?
Okay, so compared to what again?
Okay, so how important the internships or research and IEEE involvement are important compared to the academic grades?
Yeah, so when you talk about grades particularly, right? Your GPA matters, like 3.0 or something else. That's usually the bar. The classes you take don't matter. If you come in as an electrical engineer, I assume if it's ABET accredited, I assume you have skills of an electrical engineer. Anything that you need in addition, I would sometimes normally teach you, right, as an employer. Computers are different. Software programmers, unfortunately, are different. If I say I want you to know Python, you better know Python. If I say you want to know Java, you better know Java. An engineer is not like that. If you don't know MATLAB, we'll teach you MATLAB. We can't teach you how to follow the engineering process. We can't teach you how to have personal quality. We cannot teach you easily how to interact with other people. And so internships matter when you gain that experience of what employers are looking at across the board. Academia matters if you want to stay in academia. If you want to go into various research for that, it could make a difference. But you have to realize, at least at Caterpillar, some other companies, right?
Yeah, so what
If you
it
get your, sorry, go ahead. Let me finish. If you're going to plan to get your PhD, you have to be very selective of who you work for as a company. Some companies want your skill because you're a researcher, but they will not help you write more papers. If you're a PhD researcher, you have to continuously publish. Otherwise, the value of your PhD goes down, right? And so especially I've seen a lot of PhD students who go work for large companies and they think it's awesome. I work for this $20 billion company. And they're like, we are looking for someone to do development, a development researcher. PhDs are not about development researcher. They're academic researchers pushing the boundaries of technology. And a lot of people don't understand that. And so for PhD students or master's students that do want to approach your PhD and get a lot of papers and publications, make sure you have that hard discussion with your employer if you're going to have opportunities to be able to publish. At Caterpillar, right, we do not pay for you to get your PhD. At Caterpillar, patents matter. Papers don't. So if you have a patent, they'll support you getting a patent. If you want to write a paper, there is no support from Caterpillar writing a paper unless we're required for you to do one because of a partnership with the government.
Okay, so what advice would you like to give to the leaders who want to create a real impact in their own communities?
Figure out what you need or who you are. Everyone has different impact. Everyone is drawn to different problems. You have to figure out a correlation between you and the problem, right? Some of the issues is when you, and I've done this too when I work for employers, you assume their problem, right? I work at Caterpillar. I need to solve Caterpillar's problems, right? And sometimes that's nice to have that level. I'm not saying you shouldn't, but you also have that line of saying, what are your problems you want to fix in the world? Because your problems you want to fix in the world might not align with Caterpillar's business or might not align with other companies' business. And so if you want to be a leader, you have to know, can you reach that balance between what's in it for you? We're not talking money when I say that. We're talking about what is the purpose of your life that you see, right? Who do you want to be? And how does it align with who you work for? And it maybe aligns for this company, maybe it aligns for another company, maybe it aligns for this job versus another one, Maybe you have to go and do your own thing. All of that is open. But until you take that time of that self-discovery, you might go and just chase a job because it gives you money, or you might chase a job because it's a location. And then probably 10 or 15 years later, you realize you spent 10 or 15 years there, and it really has not solved something you wanted to fix when you were in your 20s. Right? And so I've had a lot of people, and I've had this in healthcare. It's awesome. Normally you see doctors would do this, or lawyers or something else like that, or other type of professions, where if you talk to a doctor or something and you ask them about their career, and you ask them, how was it? Have you ever felt that one day or one time where you had this feeling of this is why you were a doctor? A patient you saved, or something else like that. This, when you say, worth all the pain and suffering, right? Worth all the death, this is why I chose this profession. This is what my purpose was. A lot of times engineers don't look for that. And sometimes you can get it. But we look for, no, we're just solving a problem. Yes, but what problem can you solve that will make you feel this is why I became an engineer? Because you can fix those problems too.
Yeah, it's quite goal-oriented, and a strong-headed person would be going for that.
Yeah.
Thank you for the advice. So, like, we are close to the end of this session. So, let's have a rapid fire fun moment. So, like, we'll have a flash fire round.
Okay.
So, okay. So, the first question is one technology that will dominate the next decade.
AI.
Okay. And a book or a resource which every engineer should read.
It will have to be on ethics or purpose of life.
Okay. So, and one emerging technology that excites you the most.
Right now it's quantum.
Okay. One
Not
skill.
quantum software, but quantum hardware infrastructure too, quantum physics itself.
Okay, so one skill that every future engineer should have.
How to deal with difficult people.
Okay, and your favorite IEEE memory.
My favorite IEEE memory would be my first engineers week. We actually, I had these old RC cars. This is when Nintendo had the Power Gloves, which is ultrasonic cars. And I did that at Student Union, and all these kids in business and stuff could drive cars with using their gloves, using their hands, and they thought it was awesome. They thought it was magic. It was engineering.
Okay, and if not engineering, what career would you choose?
Education.
Okay, and one hobby that helps you to stay creative.
Hobby. Chess.
And if you could give one superpower to the future engineers, what could it be?
Resilience.
Okay, so thank you so much, sir. That's an end of today's session, and thank you for sharing your this visionary advices. And we are so happy that you are here and you have given your precious time to us. So
Hey, thank you.
thank you so much, sir, for joining.
Okay, bye.
Bye bye.